All right, so a bunch of things I want to go over today. The first is I want to talk a little bit about PA2 and what it looks like when PA2 starts as far as dealing with arguments. So remember, there's two ways we can run PA2. We can say PA2 and type in a number, and that's the number of sticks we want to use, or we can just say PA2 and the program should ask how many sticks. And we type in some number. So let's just think about what this looks like flowchart wise. There's some initialization in the beginning, right? We don't need to worry about what that is. But at some point, we need to know, is there an argument? So argc, in this case, is going to be equal to what? If you say PA2 number, what is argc going to be? It's either 1 or 2. For bash, it would be 1. For C, it's going to be 2, because it just counts the number of arguments. If you just say PA2, argc is going to be equal to exactly 1. Okay, if argc is equal to 2, how do we get to this argument using argv? It's argv bracket 1. Okay, don't try to memorize that. Try to figure out why this is a 1 and this is a 2 and this is a 2 so that it makes sense to you. Okay, it's an array, 1, 2 things in it, so the first element is 0, the second element is 1. You'll bump into this again and again and again anytime you use arrays in a programming language, because most arrays start from 0. All right, so the first thing we want to know is there a command line argument? We don't want to ask how many sticks do you want if they already told us when they ran the program. So we might do something like, is argc equal to 2? And if it is, then we know how many sticks they want. It's argv bracket 1. Right? So how do we convert that into an integer? We can do something like scanf. I didn't leave enough space. %d and address of some variable like num. So scanf argv bracket 1 quote %d ampersand num. And how do we know if they typed in a valid integer or not? Yeah, check the value of r. Make sure it's exactly 1. So is r equal to 1? If not, error, goodbye, and just return from your program. But if r is equal to 1, then we know that num, or whatever variable we put in the scanf, has the number of sticks they want. So now, is num bigger than or equal to 1, less than or equal to 3? And if not, error, bye. If yes, then we go ahead and we start playing the game with num sticks, right? And that's all if argc was equal to 2. If argc was not equal to 2, see if it's equal to 1. That would be this case. If it's not, that's an error. Goodbye. If argc is equal to 1, ask them how many sticks. How do we read input from the user in a C program?
Scan?
fgets before that. So do an fgets. And store that into, you know, some character array, str, whatever, and then do an scanf. And basically all of this stuff that we did here, we got to do over here again. Check the return from scanf. If it's not 1, it's an error. If it is 1, take the value that we stored their input in, see if it's between 1 and 3. If it's not, it's an error. If it is, go on, and now we can come together and play the game. Right? So that looks like a lot of code, right? It is a lot of code. If you try to write this code without something like this in front of you, chances are it's going to get confusing. Okay? Trying to figure out if this is correct is a whole lot easier than looking at a bunch of if statements and curly brackets and indents and gets and argcs and argvs and all of that and trying to figure out if it's correct or not. This is just for the very beginning. How many sticks are we playing with?
Okay, so
Oh, my bad. Is num legal? Okay, thank you. So yeah, is it a positive integer? Or is it at least 10? Thank you.
is it greater than 0?
Yeah, it's up to you. I think I said any number is fine. But definitely if it's negative, that's illegal.
After the first argument on the yes, what does that all say?
This blob,
Yeah.
scanf.
Okay.
So convert their argument, argv bracket 1, into an integer. Save the return value from scanf. I call that r, and then check the value of r. So you don't want to take this and write your code from it. Okay, this is why I'm making it kind of vague and not C, but more pseudocode, right? Don't just take this and say, okay, here's how I got to write my code. Write this yourself, right? Because you absolutely have to understand it 100%. Random person wakes up in the middle of the night, says, $1 million, if you can explain this flowchart to me, you got to be able to do that, okay? You really, really, really want to know exactly what's going on here. And if you don't, that's okay, but you got to figure it out, right? Ask questions, talk to people, things like that. Because once you understand your flowchart, right, writing the code is a matter of translating each of these blocks into C statements. And that's mostly a mechanical process, right? That's stuff you learn in 121. I want to input from the user, okay, I have to say f gets. Well, what are the arguments? I don't know. I'll go look up in my notes, or I'll look at the man page, right, and figure out what that third argument's supposed to be. But it's all about figuring out the flow. And so all of this, right, we got a bunch of if statements, we got a bunch of different return locations. That's just processing how many sticks do we want to play with. All right, and you can do the same thing once the game is playing for how many sticks do you want to pick. Right, well, it doesn't come from argv, it's always going to be an fgets, and then an scanf, and check the return value, and then check the number that was input, and make sure it's in range. And if it's not, in that case, we have to go back and ask again for the number of sticks. So we've got a loop thrown in there also, right? But figure out what it's supposed to do first, and then code it. All right, other questions on this? All right. So ODP 411, actually posted last night. Again, you're writing a C function, not a main program. Okay, you're writing a function called parse. It takes a string, which is a pointer to a character. It returns a single integer. And your function reads that string and checks to see if it's the integer 1, 2, or 3. So you have to convert that string into an integer using scanf. If the integer is equal to 1, 2, or 3, just return the integer 1, 2, or 3. Otherwise, return a -1. if it's a number that's out of range, if it's not a number at all, if it's an empty string that has nothing in it, return a -1. Okay, but if it's, the character 1 or 2 or 3, return that integer. And use scanf to do the conversion. Don't look at the ASCII codes and see if it's equal to 49 to 50 or something like that, okay? It's an scanf exercise. And the general rule is if scanf can convert that string into an integer, it's an integer, okay? But for example, if you type in something like 2.7 and you feed that to scanf, it'll say, yeah, that's an integer, it's the integer 2. Okay, that's fine. Take it as the integer 2. If they say that the number is 3, scanf will say, yep, that's the integer 3. Right? scanf starts at the beginning of the string and it says, okay, is this first character part of an integer? Is the second character part of an integer? And it keeps going as far as it can until it's no longer seeing something that's part of an integer. And if it saw anything that was an integer, that's the value it will store, and it'll return a 1. Okay? That's all the error checking you have to do. Don't worry about the fact that they typed in an integer followed by other stuff, right? So you don't really need to do any syntax parsing yourself. Just pass the string to scanf, convert it with a %d, see if it returns a 1. If it does, you can say the input's good. Okay, so don't give yourself extra work. So same as before, write your own test function to test this. How do you test it? I don't know. Call parse with an argument of quote 12, call with an argument of quote 2, call with an argument of quote -1, call with an argument of call with an argument of quote, right? Just try all the different cases and see if it returns the correct value that's specified. If it does, go ahead and build a test bed. So compile it with /temp odp 411 main.o. You can call the output whatever you want, but then assess with that output name and the name of your source program. And you should get 10 out of 10. All right. Any issues with Lab 1? So I think the kits are all fine. I had an email from someone couldn't log into kit 409. I went in and I hooked that up, and the password is back to what it should be. So you should be able to log into that. And I've graded some of the lab assignments, but I haven't finished them all. So let's look at Lab 2. So big change on Lab 2. Everybody has to write their own lab report for this one. Okay, the group thing didn't work out nearly as well as it did in my brain. There were all kinds of logistics that came up, and it ended up being this big sort of quagmire. So Lab 2, you can work on it in groups, okay, but the group dynamics are totally up to you. I'm out of it, okay, unless there's something dire going on that you need to talk to me about. But I didn't sign up for a group. What should I do? Find a group to work with. Okay, my team members never show up, and I don't know who they are, and I think they're from another planet. What should I do? Find another group to work with, or post something on the discussion, right? And I can help you with this, but I'm not the person who puts people in groups for Lab 2. Okay, it's totally up to you. The reason we're doing groups is because we only have 17 boxes. Right, and we've got 65 people in the course. Otherwise, I would just give each person your own box, but we're not there yet. So you've got to share the resources basically. But your lab report has got to be your own. Okay, so your own write-up. And what do I want in a lab? I want a report. Okay, I'm not saying you've got to have lessons learned and a new experiment and how much time did you spend or stuff like that. But it's got to read like something more than a homework problem. Okay, so a homework set. You would typically say, CSE 224, Nick Macias, 1 dot, 12 processes, 2 dot, 8 gig, 3 dot, blah, 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 right? That's how you do a homework assignment. A lab report is different. A lab report you can hand to somebody, they can read it, and they can understand exactly what you did. So if you hand somebody a piece of paper and it says 3.12 processes, what does that mean? I have no idea. Okay, here's how you can turn that into a lab report with 1 or 2 sentences. For the next part, we were asked to figure out how many tasks were running on the Raspberry Pi. We used the top command, it reported 12 processes. Okay, now somebody can read this and they know exactly what you did. Oh, we're trying to figure out how many processes, how they do it, they use the top command. Okay, now they know exactly what was going on. Okay. Next, we were asked to use raspi config and discuss 3 options in there. The first option was blah blah, which changes the password. The second one was blah blah, which enables Wi-Fi. Does that make sense? Okay, so same drill from 250, 270. You want someone to be able to take this and basically reproduce your work. But I'm not putting in, you know, all these requirements for you have to have a theory section that discusses, you know, the background theory of the material and conclusions and all this kind of stuff. Just tell the reader what you did, okay, and observations and things like that. Include code, right? So we wrote some code and it made some lights blink. Got to put the code in there, okay? You got to do a little bit of wiring, put in a circuit diagram. Doesn't have to be formal or fancy, right? But you're going to be connecting to the side of this Raspberry Pi, so you got to like tell me which holes you put the wires in, right? So sort of the obvious stuff, hopefully. So if you're working in a group, you can work on the code together. One person can build a circuit, someone else can build the code. You can all get together and debug it. It's up to you how you want to split that up, right? And since 3 or 4 people might be using the same code, you can have the same code in your lab report. That's fine. If you draw a circuit diagram, right, you can have the same picture of the circuit diagram in your lab report. That's fine. You're getting a sign-off at the end saying that this worked. You can have the same picture of the signature sheet, okay? But everything else has got to be your own. So introduction, what are we doing, what happened, what did we observe? It's got to at least be your own words, okay? All right, so let me show you lab 2, and then we'll go through the details. So let's see if I can do this. Wow, that booted fast. I guess it was already up. All right, so lab 2 is a shell script. Okay, it's a bash script. And here's what it does. It prints out a random math question. Okay, 6 + 1 =, and you type in the answer, hit enter, and if you get the answer right, the green LED lights up. All right, so it says, yeah, you got it right. And then it gives you another question, 8 + 7. Well, that one's always confusing to me, so I think it's 13. If you get the answer wrong, the red LED lights up. Okay, and that's all it does. So you can get hours of entertainment out of this, and you don't even need a Wi-Fi connection. All right, cool?
Yeah.
All right, so let's look at all the wordage. So it's like a hello world, basically, but it's a little more fun. So first thing, connecting hardware to the Raspberry Pi, there's a connector on the side. It's got 40 connection points. And it's not a little hard to see. It's extremely hard to see like this. But if you look at yours, you'll see embossed on the side, there's a little number 1 up here and a number 2 down here. Okay, so this collection of holes, this is number 1 and number 2. This will be 3, 4, 5, 6. This will be 39 and 40. Okay, and it's just 1 and 2 that are labeled. And those holes, those numbers, correspond to this picture in the lab. Okay, so this is 1, 2, 3, 4, 5, 6, 39, 40. And these have different functions. So pin 2 and 4 are labeled 5 volts DC power. Okay, you don't actually need to use those. Pin 6 is labeled ground. Okay, so that you'll probably need to use. And in particular, pin 16 is labeled GPIO 4, 18 is GPIO 5, 20 is ground. So let me mark those over here. We'll come back to those in a second. All right, so mostly you have these GPIOs, general purpose I/O. These are ports that you can use to either write a voltage to or read a voltage from. They're how you get out of or inside the box from the outside world. But there's other things on here. There's this thing called I2C. It's a serial protocol. There's SDA. It's another serial protocol. There's ways to do terminal communications through a serial link. And pulse width modulation, everyone's favorite, right? Pulse width modulation 0 is down here. But mostly we're going to just deal with the GPIOs. So GPIO 4 corresponds to pin 16, et cetera, et cetera. That's what I just said. Okay, word of warning, don't ever connect a voltage source to this. Don't hook it up to a power supply. Don't take the 5 volts out of here and connect it to anywhere else, okay? They're fairly robust, but if you were to hook 5 volts up to one of these from a power supply, you'll probably fry that I/O line, and then you have to use a different one from that point. And it's not a huge deal. It's a $5 unit inside, but it's an inconvenience in the middle of the term. So, all right. So, let's see. All right. So let me kill this. So there's a command available on these called GPIO. It's a bash command. You can run it from a bash script, and it lets you do different things with those I/O lines. And there's only 2 commands we need to know about. The first is GPIO mode. So we say GPIO space mode space the number of the GPIO port space, and then you can say in or out to say we want to do input or output on this line. For this lab, we're writing voltages to the ports so we can light up LEDs, so you want to say out. So GPIO mode 4 out, GPIO mode 5 out. And then when you want to actually write a value, you use GPIO write, the port number, and then either a 0 or a 1. And that'll push that pin to either 0 volts or 5 volts. So we can build a really simple circuit as follows. We can take GPIO 4, which is on pin 16, go through our 1K resistor, go through an LED, and connect this to ground, which is pin 20. And then we can take pin 18, put that through a 1K resistor, put that through an LED, connect the other end to ground. There's your whole circuit. Okay, so it fits on, the tiny little breadboard. So no nightmares about wiring circuits for this course. 2 LEDs, 2 resistors, 1, 2, 3, 4 wires, I think. But once you have this built, if I say GPIO write 4, 1, it should put 5 volts on GPIO 4 pin 16, 5 volts, this ends ground, that should light up. And if I say GPIO write 4, 0, that LED should turn off. So let's make 4 an output and make 5 an output. So if I write 4 as a 1, that turns that LED on. If I write 4 as a 0, it turns it off. 5 is already turned on. If I write a 0, it turns off. If I write a 1, it turns on. And that's all there is to controlling these. And these commands, you can put them inside shell scripts. They're just bash commands. All right, so experiment 1 is what I just did those past 30 seconds, right? Hook up these 3 pins, 16 and 18 go to the positive side of an LED, 1K resistor. Pin 20 goes to the negative side of the LEDs. Use these 2 mode commands to set those to be outputs, and then play around with the write commands. Write at 1, it should turn on. Write at 0, it turns off. Okay, that's just making sure you've got the GPIO system working, you got the mode connected, you got these wires hooked up physically in the right way, your LEDs aren't reversed, all of that stuff. Okay, and you want that to all be working before you start writing bash code. Because if your add program's not working correctly, you don't know if it's a wiring problem or code problem or what. So do this first. You don't need to get a sign off for this. This is just kind of a warm up. And then the actual math quiz circuit. So write a bash script, print simple math problems, wait for the user to type an answer and hit enter. If it's correct, you get the green. If it's incorrect, you get the red. And the LED stays lit until they put in the answer to the next question, right? So you don't have to like turn it off or anything. All right, if you want to generate random questions, the easiest way is with this variable called random. So $random gives you a random number. And every time you do this, it gives you a different random number.
Is there an upper limit for the random number?
I think it's 32767. But since we want our quiz to be a little easier than that, we want numbers from 0 through 9. How do we change this into a number from 0 through 9?
Remainder.
Yes, remainder. So let's just do $paren random %10. And so now we get a number from 0 to 9. Yeah.
Since it ends at 32 something 7, wouldn't 8 and 9 have slightly?
Yeah, they have a slightly less chance. How would you fix that?
Divide by that over 10 and then try.
That could work. It might still be biased. You could pick off the second digit, maybe.
You could do, what was the maximum?
32767, I believe.
32627?
767.
767. It
Yeah.
ends in 7. So you can probably plus 3 to the random, then do the remainder term?
Then you might be biasing against 0, 1, and 2.
Oh, yeah.
Are we supposed to include 0 in our math?
Well, it's up to you.
Between 10 and 1.
If some people have a hard time with 0, so it might be good to include, but it's up to you. You're going to demonstrate this to someone in the lab, so they need to be able to answer the questions. So don't ask them what the square root of 519 is or something. But if you do this, it'll include 0, right? Because modulo can give you as low as 0, as high as 9. All right, so you can generate random numbers. So generate 2 random numbers, print them out with a plus sign in between equals, wait for the user to type something in, and then compare their answer to the sum of those 2 numbers. So you got to do a little bit of arithmetic in bash, and then a comparison. And then if it's right, do GPIO 5. If it's wrong, do GPIO 4, or whichever way the red and green are set up. All right, and then once that's working, go ahead and get a signature. So there's a sheet here you can print out and get somebody to sign these 3 observations. So first, each time that you get a question, it's saying A plus B equals some number, and it lets the user type an answer, right? And then if the answer is correct, the green LED turns on. If it's incorrect, the red LED turns on. So you just want to demonstrate this to someone, show them a few cases of each, get a signature, initials next to witness, date it, put your group members, and you're good to go. Yeah?
Does that be the lab assistant, or could it just be anybody in there?
It can be pretty much anybody in there, lab assistant. You can grab Izad, you can grab me. You can grab somebody from another group if you want, if there's nobody else available. If it's like, absolute emergency, 11th hour, life or death, you can have somebody else from the group witness it, I suppose, because I trust you, right? It's just practice and getting a sign off on it. So, but it's cool to demo it to other people too. All right, you got 2 weeks to do this, man. Right? You could you could write one line of bash code a day and still get this done before the deadline, okay? But the sooner you get it done, right, you don't have to worry about it after that. And you don't have these situations where it's due tomorrow and you can't find the lab kit or you can't get logged in and you got to find me to reset it or stuff like that. So get it done early and then have a vacation for a week and a half. All right. I also posted a note about screen size on the Raspberry Pis. So if you change your screen size at all, if you maximize it, things like this, VI acts a little weird. It doesn't use the whole screen, or lines start to appear on top of other lines or things like that. So if you're noticing any weirdness, go to this announcement and follow what it says. Basically, you want to set the size of the window by dragging a corner, not by maximizing. Figure out how many rows and columns you have, and then use this bash command, stty, cols, number of columns, rows, number of rows. And that seems to make it totally solid. Okay, at least on Windows and Linux it seems to work. So if you're finding weirdness, go back and check that note. So I posted a note about scholarship opportunities, Foundation Scholarship. Deadline is coming up quickly, but take a look at that. And I posted a Git video. Okay, so it's 11 minutes of happiness on how to use Git, how to initialize, how to check things in and commit them, and how to connect to GitLab. Okay, it does not talk about the stuff we talked in class about what Git is, why you want to use it, the idea of source code control repositories. I'm not going through any of that. Okay, it's purely the mechanics of how do you do the one-time setup to authenticate with GitLab, to tell it what your username is, your email, and what editor you want to use, and then the steps that you go through each time that you want to put something new into a repository or start a new repository. Okay. Again, strongly recommend every project, every assignment, every lab that you do in this course or forevermore, put it in its own directory. Okay. You really want to organize, because you're writing stick.c and you compile it and you call the output stick, and if that's in the same directory as PA1 and PA1 was called stick, you've lost your original PA1 stick, right, your script. Separate directories, right, keeps things nice and clean, and it works really well with something like Git because you can push all of these things off and things won't get confused. All right, so let's talk some more Linux. So you know the command who? So who shows you who's logged in. So that can be useful. This gets really long right before an assignment is due. I'll see like 40 or 50 entries here sometimes. But it gives you a username. PTS tells you where they're located. It's not terribly useful. This tells you when they logged in, right? And this is the IP address that they logged in from. 192.102, that's usually intranet, right? It's something on campus. Finger gives you details on a user. So if I say finger Nick, it tells me my login, my full name, the shell I'm using, my directory. This one has my office and my phone number, when I logged in, and how long I've been sitting around not doing anything. And if I have mail, it'll tell me that I've got unread mail. And so you can make a file in your home directory called .plan, and you can put your plan in there. And then when you finger somebody, it'll tell you what their plan is, right? So this used to be like when we were collaborating on projects and stuff. You could say what your project is and what your plan is, and you could, you know, sort of keep in touch with one another that way. So there's a .plan and a .project, and that'll tell you your project. And so again, Linux was sort of built with this idea of kind of a cooperative environment, right, where people could work on things together and so on and so forth. So who from here is logged in? All right. So try the following command, write space Nick, and hit enter. All right, so you can send me messages. And you can type whatever you want, and then it should show up. I'm getting lots of messages here. All right, so I can write back to people. All right. There we go. Yeah, but everybody knows now, and I don't know which one you are. So MESG says, are you available for people to talk to you? And by default, it's yes. If you say MESGN, right, then that should stop people from being able to talk to you, unless they're already talking to you. But if I try to write to Nick, then it'll say messages are disabled. So if people are bugging you, you can say MESG space N and turn that off.
Oh dear.
How do you get out of it just as an extra thing?
And yeah, you can Control C or Control D out of right. All right. There we go. All right, so let's talk about pipes. So one of the ideas in Unix was that you could put commands together, right? And normally when you run a command, like, let me show you a command word count. So WC is word count. This is a test. Cool. Bye-bye. And when I finish typing an input, it prints out 3 numbers. The first number is the number of lines of input. This is a test, cool, bye, 3 lines. The second is the number of words. This is a test, cool, bye, bye, 7 words. And the third is the number of characters. So word count, you can give it the name of a file, and it'll tell you how many lines, words, and characters in that file. But if you just say word count, it basically reads from standard in and then does a word count on that.
What's the separator it uses for the number of words?
Spaces. Probably any white space, tabs, new lines. All right, now ls is a command that shows me my files, all right? ls-l shows me a bunch of information about my files. So if I were to count the number of lines in this output, that would tell me how many files I have in my directory, right? So here's what I can do. I can say ls-l, and I can say pipe that into word count, which means ls-l generates output to standard out to my display. I'm saying instead of showing that on my display, feed that over to the input of this next command, word count. So I'm basically saying I want to run word count on this ls-l. And it tells me I got 11 lines of output. And it's a little deceptive because when I say ls-l, it gives me this one line in the beginning which says total, right? ls is a weird command. If I pipe ls into something, it'll actually print one file per line instead of printing, across in nice rows like that. So if I take ls and put it into word count, it gives me a 10. That's how many files I have in my directory. If I say ls/bin, pipe it into word count, I can see there's 137 files under /bin. So there's probably a switch on ls that'll tell you how many files are in a directory. I don't need it, right? If I know this word count command and I know how to pipe, right? So how many people are logged onto the system? I can just take who, pipe it into word count. There's 13 people logged in. So this starts opening up a lot of possibilities, right? I don't know if this will work. There we go. So I took the date command, and date normally displays on standard out what the current date is. But I said date, pipe it into cowsay, and it said, okay, instead of displaying date on my display, send that to the input of the cowsay command. And cowsay read the date, and then my cow said what the date was. So I can have my cow show me my contents of my directory. And in fact, I could take that and I could pipe it into write Nick. And now I just got a message with a talking cow. So we can use pipes to combine commands, basically. And if you start thinking of that capability, you'll start finding all kinds of ways that you can use this. The other thing is we can take standard out, and instead of displaying it on our display, and instead of piping it to the input of another command, we can put it into a file. Okay, and the way we do that is with a greater than sign. So if I say date greater than haha, I don't see the date on my screen anymore, right? But in my current directory, I see something called haha, and if I were to look at that, I'll just go into VI. It's got whatever the date was when I ran that date command. If I say ls-l greater than haha, and I look at haha, it's a copy of my listing. So we can take the output of commands and we can save them into files. And we can use a less than sign to feed standard in from a file. So that instead of waiting for us to type something, it reads the input from a file. And that's really useful when you're debugging code and you want to use the same test case again and again, and it needs you to type 10 lines of stuff. You can put all that in a file and then just say program less than sign file name, and it reads from that input. So this is all in the realm of input-output processing. So command 1, pipe, command 2, basically says take standard out, feed that to one end of a pipe, and on the other end of the pipe, connect standard in of this second command. If you use a greater than sign, basically says take standard out, but in some sense write that into a file. And if you say command less than file, basically says take this file and send that to standard in. And you can do both. You can run a command and say standard in comes from this file and standard out goes into this other command. And that other command's output should go into a file. You can chain these things together pretty much any way you like.
So phi is number of phi,
So file is just the name of a file.
plus number.
Unless your file name is a number, it's just a name. But it could be a number. Alright, so now I've got a file named cow, which has a talking cow inside. Alright, makes sense? So these are things to play around with, right? Just mess around with them and you'll find tons of ways that you can use them. And they'll start to get more useful the more you experiment with them. Alright, so we are out of time.